3I Atlas, a third ever interstellar object observed from Earth, currently racing through our solar system. Now, astronomers have captured that moment live, streaming in real time.
On the 1st of July, 2025, astronomers using the Asteroid Terrestrial-impact Last Alert System, or ATLAS, detected a fast-moving object on a sharply hyperbolic orbit, soon confirmed as 3I-ATLAS, the third known visitor from beyond our solar system.
3I Atlas is moving closer to the sun. There's still so much we don't know, and with the sun's...
Back in 2017, 1I ʻOumuamua's peculiarity led Harvard astrophysicist Avi Loeb to suggest it might have been an artificial probe. Loeb is now making a similar case for 3I-ATLAS. Now, NASA has finally responded to claims that 3I-ATLAS is an advanced alien spacecraft. There's a lot to unpack. Let's get started. 3I Atlas. What we know so far? 3I-ATLAS is the third interstellar object ever confirmed to pass through our solar system, following 1I ʻOumuamua in 2017 and 2I Borisov in 2019. At the time of its discovery, this visitor was about 4.5 astronomical units from the Sun, roughly the distance of Jupiter's orbit. Astronomers quickly calculated its path and found it to be hyperbolic, meaning it is not bound to the Sun and is only visiting once before heading back into interstellar space. Its orbital eccentricity is about 6.1, far higher than the value of 1 that separates bound orbits from unbound ones. It will reach its closest point to the Sun, about 1.36 astronomical units, on 29th of October 2025, then move outward again. The object is moving extraordinarily fast, traveling about 58 kilometers per second relative to the Sun, which equals roughly 130,000 miles per hour. Its orbital inclination is nearly 175 degrees, meaning it moves on a steep retrograde path, almost opposite to the general direction of planets and most asteroids. These figures alone confirm that 3I-ATLAS came from far beyond our solar system. NASA's Hubble Space Telescope and other observatories showed that the object is surrounded by a glowing coma of dust and gas, evidence of active sublimation as sunlight warms its surface. Early estimates place the nucleus at no more than 5.6 kilometers across, though it could be as small as about 440 meters. Most of the light we see comes from the surrounding dust, making precise size measurements difficult. The more we get to know about this visitor, the more it astonishes us. 3I Atlas began to show comet-like activity while still very far from the Sun. Data from the Zwicky Transient Facility indicate that it brightened as early as 9 astronomical units from the Sun, a distance where water ice remains frozen. This suggests the presence of more volatile materials such as carbon dioxide and carbon monoxide. NASA's James Webb Space Telescope confirmed this in August 2025, detecting a coma dominated by carbon dioxide, along with water, carbon monoxide, and dust. The ratio of carbon dioxide to water is about 8:1, far higher than typical comets in our solar system. Back in 2017, ʻOumuamua followed a hyperbolic path with an eccentricity of about 1.2 and an inbound velocity near 26 kilometers per second relative to the Sun. Unlike 3I Atlas, ʻOumuamua showed no visible coma or tail, leaving scientists to debate whether it was an asteroid, a comet that had lost its surface volatiles, or even something stranger. By contrast, 3I Atlas clearly behaves like a comet, with strong outgassing, a bright coma, and well-defined chemical signatures. 2I Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov in Crimea, was more like 3I Atlas. It too displayed a prominent coma and tail, leaving little doubt that it was a comet. Its eccentricity was about 3.36, and its speed relative to the Sun was about 32 kilometers per second, noticeably slower than 3I Atlas, but still unbound. Spectroscopic studies of 2I Borisov revealed a composition similar to solar system comets, including water, carbon monoxide, and dust, though with some unique ratios that hinted at different conditions in its home system. In many ways, 3I Atlas looks like a larger, more volatile rich cousin of 2I Borisov, but moving nearly twice as fast. These comparisons matter because each interstellar object gives astronomers a rare sample of material from another planetary system. ʻOumuamua showed that not all interstellar visitors behave like typical comets. 2I Borisov and 3I Atlas, on the other hand, demonstrate that icy, volatile, rich bodies can survive long journeys between stars. The chemical signatures of 3I Atlas, particularly its carbon dioxide dominance and unusual polarimetric properties, suggest it formed in a very cold environment where carbon dioxide ice could remain abundant. Or maybe it's something else entirely. Maybe we're missing an important piece of the puzzle. Avi Loeb's hypothesis. Back in 2017, when the object later named 1I ʻOumuamua was discovered by Pan-STARRS in Hawaii, Harvard University astrophysicist Avi Loeb raised questions about its nature. He pointed out that ʻOumuamua showed non-gravitational acceleration. That is, its trajectory deviated slightly from that predicted only by gravitation from the Sun and planets. He also observed that ʻOumuamua manifested no visible cometary tail, despite approaching the Sun. These anomalies led him to explore whether radiation pressure from sunlight might explain the acceleration if ʻOumuamua had an unusually high area-to-mass ratio, perhaps being shaped like a thin sheet or disk. Loeb co-authored a paper with Shmuel Bialy in October 2018, proposing this solar radiation pressure hypothesis. They estimated that to explain the observed acceleration, the mass-to-area ratio of ʻOumuamua would need to be on the order of 0.1 grams per square centimeter. Loeb is a career scientist with a strong background. He is the founder of the Galileo Project, which aims to search for evidence of extraterrestrial technological artifacts. He is also a fellow of the American Academy of Arts and Sciences and the American Physical Society, among others. His books, Extraterrestrial, The First Sign of Intelligent Life Beyond Earth and Interstellar, The Search for Extraterrestrial Life and Our Future in the Stars, elaborate his viewpoints on the possibility that some interstellar objects may be artificial in origin. Loeb has persisted in arguing that some unexplained features warrant considering artificial origin hypotheses. He has also claimed that the statistical properties of Oumuamua's velocity relative to the local standard of rest are unusual. It appears to have had very low radial and vertical velocity relative to nearby stars, which Loeb argues is less likely if its motion were purely natural. When 3I Atlas was discovered, Loeb again raised hypotheses that go beyond the standard natural comet interpretation. One of his core claims is that 3IATLAS's trajectory and parameters may be difficult to reconcile with a purely natural object, and that some features are suggestive of an object sent intentionally, possibly a probe or artifact of advanced extraterrestrial intelligence. Loeb has pointed out that the orbital plane of 3I Atlas is retrograde, meaning it moves opposite to the general motion of solar system planets, but is tilted only about 5 degrees from the ecliptic, that is, the plane of Earth's orbit around the Sun. He calculates that the odds of an interstellar object, by chance, having such alignment are very small. Another of his claims is related to timing and observation geometry. Loeb observes that 3IATLAS's perihelion, or the point of its closest approach to the Sun, around 29th of October 2025, will occur at a time when, from Earth's perspective, the object is near the Sun, meaning it will be harder for Earth-based telescopes to observe it when it is brightest. Loeb has suggested that this could be a strategic or deliberate characteristic if the object were hiding certain features during its brightest phase. Loeb also argues that 3IATLAS's high speed is another feature that demands scrutiny. He claims that such speed, combined with other factors, could offer benefits for stealth or reconnaissance if the object were an artifact. For example, a high velocity makes interception or study more difficult, and moving quickly reduces exposure time to scrutiny. In addition, Loeb claims that the path of 3I Atlas brings it relatively close to 3 planets, Jupiter, Mars, and Venus. He proposes that these close passages might enable or facilitate deployment of gadgets by a hypothetical extraterrestrial intelligence. He uses these close approaches to strengthen his argument about how the trajectory could be beneficial for an intelligence wishing to observe, monitor, or interact covertly. Despite all of this, Loeb has also publicly stated that he considers the possibility that 3IATLAS is a comet to be the simplest hypothesis. He frames much of his more provocative argument as a pedagogical exercise in pushing boundaries and testing assumptions. Well, there is a basis for that kind of thinking. Alien probes, Fermi paradox, and the zoo hypothesis. In 1950, during a lunchtime conversation at the Los Alamos National Laboratory, physicist Enrico Fermi famously asked, "Where is everybody?" He was referring to the apparent contradiction between the high probability of extraterrestrial civilizations and the complete absence of any confirmed evidence of their existence. Our Milky Way contains an estimated 100 to 400 billion stars, and astronomical surveys such as the Kepler mission have shown that many of those stars host planets within their habitable zones. Life on Earth arose relatively quickly after the planet cooled, and intelligent life developed within roughly 4.5 billion years of Earth's formation. These numbers suggest that other intelligent species should have had plenty of time to evolve, develop technology, and explore the galaxy. Yet humanity has found no undeniable signals or artifacts. This is the Fermi paradox, but maybe there are others, and we simply don't see them. Advanced civilizations might rely on physical exploration rather than direct communication. Researchers have explored the possibility that interstellar travel by robotic devices, sometimes described as self-replicating probes, could be far more efficient than sending radio messages across the void. Keith B. Wiley's 2011 paper, The Fermi Paradox, Self-Replicating Probes, and the Interstellar Transportation Bandwidth, calculated that a single fleet of such machines, capable of making copies of itself using local materials, could spread through the Milky Way within only a few million years. This may seem like a lot, but remember, life on Earth is 4.5 billion years old. If even one civilization in the galaxy developed this technology, it could theoretically have seeded probes throughout the stars long before humans evolved. The absence of obvious probes, therefore, deepens the paradox. Some scholars imagine that these hypothetical machines would not simply wander aimlessly. In a 2018 paper, astronomer John Gertz suggested that a network of nodes, or essentially interstellar relay stations, could be positioned around the galaxy to collect data, watch emerging civilizations, and pass along information to their creators. These nodes might communicate with one another using tightly focused beams or other methods invisible to us. Earth could already lie within the watchful sphere of such a network without ever noticing a thing. Physical artifacts, according to this model, might be more reliable than fragile radio links for monitoring distant planets over millions of years. Another influential explanation is the zoo hypothesis, first articulated by radio astronomer John A. Ball in 1973. Ball proposed that advanced extraterrestrial societies may indeed be aware of humanity but deliberately avoid overt contact, much like zookeepers trying not to disturb the animals they observe. Thus, when Harvard astrophysicist Avi Loeb argued in his 2021 book Extraterrestrial that ʻOumuamua might have been an artificial object, perhaps a thin solar sail propelled by radiation pressure, he was not talking in a void. 2 years later, in August 2019, astronomers in Crimea detected 2I Borisov, another interstellar object, which behaved far more like an ordinary comet, displaying a bright coma and tail rich in familiar volatiles. That discovery reassured many researchers that interstellar objects can be natural and cometary. Now, attention has turned to 3IATLAS. Loeb argues that if a civilization wanted to send reconnaissance probes, small natural-looking objects would be an efficient and discreet way to do so. Hypothetically speaking, sending automated craft is far more practical than sending living beings. Even traveling at a mere fraction of the speed of light, a fleet of small, robust probes could gradually spread through the galaxy and monitor countless star systems. If they are built to harvest resources and replicate themselves, their numbers could increase exponentially, ensuring broad coverage within a few million years. For civilizations millions or billions of years older than ours, this would be a simple strategy. Our first detection of interstellar visitors could therefore be indirect evidence of such exploration, even if the probes resemble natural objects. But what does NASA have to say about all of this? NASA's evidence-based response. From the moment the object was first detected, astronomers began a coordinated effort to track its motion and study its physical properties. Follow-up observations came quickly from facilities including the 8.2-meter Subaru telescope on Mauna Kea, the 10-meter Keck Observatory, the European Southern Observatory's Very Large Telescope in Chile, and NASA's own Hubble Space Telescope. These instruments measured 3I Atlas as it passed through the inner solar system on a sharply hyperbolic path, indicating beyond doubt that it originated outside the Sun's gravitational influence. The first question scientists asked was whether 3IATLAS behaved like a comet or like something else entirely. High-resolution images revealed a classic coma, or the cloud of gas and dust that forms when volatile ices vaporize, as well as a distinct tail stretching more than 200,000 kilometers. Spectroscopic measurements using the Keck Observatory and the ESO's X-Shooter instrument identified emissions from cyanogen, diatomic carbon, and water vapor, all common components of solar system comets. Photometric data recorded a steady light curve, with periodic dimming that matched the slow rotation of an irregular icy body about 1 kilometer across. NASA scientists emphasized that these chemical signatures and rotational patterns are exactly what would be expected from a natural cometary nucleus made of water ice and dust grains that have spent eons in interstellar space. Astrometric tracking showed that 3I Atlas entered the solar system at an inbound speed of roughly 26 kilometers per second relative to the Sun. Minor deviations from a purely gravitational trajectory were also detected, but these non-gravitational accelerations were fully consistent with the effect of outgassing jets or localized streams of vaporized ice that act like tiny thrusters on the surface of an active comet. Models developed by the Jet Propulsion Laboratory's Solar System Dynamics Group demonstrated that the observed acceleration could be reproduced with outgassing pressures of only a few micronewtons per square meter, well within the range measured for other comets such as 67P Churyumov-Gerasimenko during the ESA's Rosetta mission. In a press briefing, Tom Statler, NASA's lead scientist for small-body missions, summarized the findings. It looks like a comet. It does comet things. It very, very strongly resembles, in just about every way, the comets that we know. Statler noted that extraordinary claims, such as the suggestion that 3IATLAS might be an alien probe, require extraordinary evidence, and that nothing in the extensive dataset provided any hint of artificial origin. Other NASA researchers, including David Farnocchia of JPL, reinforced this message, pointing to the robust orbital solution and the agreement between different teams' measurements of the object's composition, size, and light curve. Independent investigations by observatories and universities outside NASA reached identical conclusions. Teams from the European Space Agency's Near-Earth Object Coordination Center, the Canadian French-Hawaiian Telescope, and the Pan-STARRS survey all reported identical spectral fingerprints of simple cometary volatiles. A collaboration led by Karen Meach at the University of Hawaii's Institute for Astronomy compared the dust-to-gas ratios of 3IATLAS with those of solar system comets and found no statistically significant differences. Even the slight reddening of its surface, derived from Hubble ultraviolet optical photometry, matches the space-weathered surfaces of long-period comets originating in the distant Oort cloud. From combined optical and infrared data, researchers calculated an effective radius of roughly 600 to 800 meters and an albedo of near 0.04, values typical of dark, carbon-rich cometary nuclei. Its mass is estimated at about 1 to 2 into 10 raised to the power of 11 kilograms, assuming an internal density of 0.5 grams per cubic centimeter, again squarely in the range of porous icy bodies. The production rate of water vapor at perihelion was measured at approximately 2 into 10, raised to the power of 27 molecules per second, nearly identical to comets like C 1995-01 at similar distances from the Sun. These hard numbers leave little room for speculation about exotic propulsion systems or engineered alloys. NASA's response also drew lessons from earlier interstellar visitors. The agency highlighted how 3IATLAS differs from 1ʻOumuamua, discovered in 2017, which lacked a visible coma and displayed an unexplained acceleration that some researchers initially struggled to model. By contrast, 3I Atlas behaves far more like 2E Borisov, the interstellar comet discovered in 2019 that produced abundant gas and dust. Statler and his colleagues argued that the clear cometary activity of 3I, Atlas, strengthens the case that many interstellar objects are icy bodies ejected from distant planetary systems during their formation, and that ʻOumuamua was likely an unusual but still natural fragment of such material. Continued monitoring is planned as 3I, Atlas, recedes toward the outer solar system. NASA's Infrared Telescope Facility and the upcoming Vera C. Rubin Observatory in Chile will track its fading brightness through late 2025, refining models of its rotation, mass loss, and chemical composition. But every instrument so far, from ground-based telescopes to the Hubble Space Telescope, has found results consistent with a standard comet of extrasolar origin. There are no anomalous radio emissions, no unexplained light curve fluctuations, and no evidence of metallic alloys or artificial structure. According to NASA, the object's hyperbolic orbit proves its interstellar origin, but its physical properties are all overwhelmingly natural. The agency encourages continued observation, since every interstellar object provides unique insight into the processes of planet formation in other star systems. However, it concludes that there is no credible indication that 3IATLAS is an alien probe. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.